Okay, these are just notes for our lecture for section 2.4, which is infinite limits. So that's where we were dividing, potentially dividing by zero. And so we're going to talk about when we get a limit that approaches positive infinity or negative infinity. I'm just going to make this a little bit smaller. And then these notes will be online. I actually encourage you to maybe download them. Some of the printing might be small. Um, and okay, so a limit exists if a function approaches a finite value, but it's also possible that the limit is going to approach infinity or negative infinity. And that occurs when we're dividing a constant by zero. So let's say we have we're graphing k over x. And as x gets really close to zero, the function is either going to go down towards negative infinity or up towards positive infinity. So let's just look at function number 2 right there, 5 divided by the quantity x minus 3. And so in number 2, what we're doing is we're looking at the limit as x goes to 3 from the right. And at number 3, we're looking at x goes to 3 from the left. And I graphed it way down here, right at the bottom. That's where I had room for this. And so, so here's the plot of f of x is equal to 5 over x, the quantity x minus 3. And so you can see as x gets close to 3, what you're doing is you keep, as it gets closer and closer to 3, you're dividing 5 by a smaller and smaller number till eventually you're getting really almost at 0. Okay, so when you're coming to x towards 3 from the left, because in that case the denominator is negative, right? When x is less than 3, the denominator is negative, so you're dividing 5 by a very small negative number. And the graph goes all the way down. You get what's called the, it goes down to negative infinity. And when x is greater than 3, so you're approaching x equals to 3 from the right. So in that case, the denominator is positive, but you're dividing 5 by a very, very small positive number. So that way the graph goes up towards positive infinity. So I always think graphing these functions is really quite helpful. You can look at the formula and try to figure it out, but there's nothing wrong with plotting to try to at least confirm your answer. And so, and it turns out the line x equals 3 is called a vertical asymptote. And so vertical asymptote is just it's a straight line that's up and down, and the function gets closer and closer to that line, but never touches it. So the plot of this function, f divided by x minus 3, it never touches. Yeah, so it's not defined at x equal to 3. So right, there's a hole at x equal to 3. So it's defined. So the domain is everything except x equal to 3. So there's actually there's no value at x equal to 3. So it gets so the graph gets as close to the line x equals 3 as we want, but never actually touches it. And it's called a vertical asymptote. And in the notes, that's denoted by the acronym V period A period. So let me just go back up here. And okay, so again, let's just look at 1. In that case, it's 5. It's being divided by, as x gets close to 3, only this time we're squaring it. So the denominator is always positive. Okay, and so in this case, whether you're coming from the left or whether you're coming from the right. So the graph of number 1, it always goes, no matter which direction you go to x equals 3, it's always a positive infinity. And I encourage you to plot that on your graphing calculator. You'll see that the y coordinate is always positive because you're always dividing by a positive number. Okay, so so some of the kind of limits that we're going to talk about in this class as we go on the course, we're going to talk about limits where we have 0 over 0. So that's where you're not so sure whether it may not go to positive or negative infinity. But if you're dividing by but if it's in the form k divided by 0, where k is non-zero, then it definitely goes to 0 infinity or negative infinity, or possibly does not exist. Okay, so why don't we just look at I'm very big on graphing and determining limits. I really think it's a good idea to graph, or even solving equations, graph the functions and see where at least you can get a rough idea where the functions intersect. But I think it's a good idea to know what the shape of the curve looks like. So when you're doing these because throughout this course, we're going to be looking at like maximum and minimum. And yeah, I think it's just a really good idea to know what the curve looks like. Okay, so in this case, let's just look at the graph of this function as x gets, okay, the first two, we're looking at as x goes to 1 from 5a, from the right, and 5b, we're looking at x goes to 1 from the left. Yeah, and you can see in that case, the graph goes to, as we're going towards x equals 1 from the right, the graph is going up. So it's that rightmost curve. The curve is in 3 pieces. And so, yeah, so at x, so as we're going to 1 from the right, yeah, the curve goes up. And so the limit is x equals positive infinity. So this would be this is what I'm talking about right here. So like right here. So that part of the graph. So you can see how it's going up. And as x is going, to x from the left, you can see that it's actually going down. So now I'm talking about, this part of the curve right here. You can see that it's going down. Okay, and then again, it's a little small to read, like C and D. To me, that almost looks like it's going to 6, but it's actually -6. Okay, so now we're looking at this asymptote right here. So now we're looking at the dotted line on the left, and you can see as we go as we go to negative infinity to -6 from the left, the graph is going down. So the limit is negative infinity, and as we go to x to -6 from the right, the graph is positive infinity. So okay, and then okay, so this is what we've learned so far in the course. So the limit is x goes to 1, like +1 from the right and the left. So going to +1, the graph goes up, it's going to positive infinity. As x goes to 1 from the left, the graph is going down negative infinity. So the limit doesn't, so as x goes to 1, the limit doesn't exist, right? Because they're not the same value. So remember, for the limit as x goes to 1 exists, the limit has to be the same from the left and the same, and the limit from the left has to be equal to the limit from the right. And in this case, the limit of a and b are different, and the limit of c and d are different. So going from so the limit of 1 can't exist because going to 1 from the left and the right are different. And the limit as x goes to -6 can't exist because once again, the limit going from the left and going from the right are different. So hopefully that's something we know by now. And if not, just please contact me if you have a question. Okay, so I think of so definitely, you don't actually have to know these definitions, but you should at least recognize, so vertical asymptote is a straight up and down line. It's a vertical line. The graph never actually touches that line. So so if f of x approaches either positive or negative infinity, as x approaches c from the right or the left, the line x equals c is a vertical asymptote. So again, this graph down here, you actually can't see, I don't actually have the line plotted in here, but that plot f divided by x minus 3. Yeah, so no matter what direction we go to x equals 3, the left or the right, yeah, so if we go from the left, it's it's negative infinity. As we go to the right, it's positive infinity. So x equals 3 is so the graph never crosses x equal 3. It's undefined at x equal 3, and and it's going to either positive or negative infinity depending what direction you're on. So the line x equals 3 is a vertical asymptote. Okay, typically we get asymptotes when we have a non-zero constant divided by, when we're potentially dividing by 0. So if you look at, and again, look at like that first problem right there, f divided by x minus 3 squared, x equals 3. Yeah, that's definitely an asymptote. And I encourage you to graph that. And I graphed a couple of these, but just use your graphing calculator or go use some kind of plotting utility online. Like we'll go to Wolfram Alpha. You can also plot that way. You get pretty good graphs from that. Yeah, and as you get close to 3, the graph, the y coordinate gets as large as we want. And I already graphed, well, something similar to number 2. Well, no, actually not. I take that back. Because there we have x divided by x minus 3. But once again, near x equals 3, the numerator is not 0. Yeah, the numerator is not 0 for number 2 when we get near x equals 3. So the problem occurs when you have 0 over 0. Okay, here. So, okay, so let's just look at this number 4. So you graph that. I mean, I'm sorry. Look at number 3 there. Okay, so you have x squared minus 4 over x squared minus 5x plus 6. And okay, well, then you factor and you see, oh wow, well, there's 2 zeros in the denominator. X equals 3 is a 0. And the denominator is also 0 at x equal to 2. So you might think, well, are those vertical asymptotes? Well, first of all, when x equals 3, we know the denominator is not equal to 0 because 9 minus 4 is non-zero. But when x is 2, yeah, you get 0 over 0. Okay, so this is a nice one to do algebraically. So you just factor the numerator and the terms of the x minus 2 terms cancel out. So when x is 2, you have 0 over 0. So that's where you're not really sure. So it's when it's a non-zero constant over 0. Yeah, then that's where you could definitely get the asymptote. When it's 0 over 0, well, then we're not really sure. Okay, so and as you can see there, yeah, you cancel out. First of all, the function is not defined at x equal to 2 because there's a hole there, right? Because you're going to get 0. F of 2 is undefined. 2 is not in the domain of problem number 3. Okay, but you can see there, if you actually graphed it as x goes to 2, the function, if you cancel out the terms of the factors of x minus 2, it's equal to x plus 2 over x minus 3. And you just substitute x equal 2 and you get 4 over negative 1. So the limit in that case goes to negative 4. In that case, you can determine the limit as x goes to 2. It's just direct substitution. Just cancel out the common factors of x minus 2. And then you can just do direct substitution and you can get that the limit is negative 4. And then you can plot that and you can see that as x goes to 2, the y coordinate gets very close to negative 4, but it's actually not defined there. And we're going to be seeing a lot of that because we're going to do these difference quotients, and we're going to take derivatives. But of course, 2 is different, right? You have as x goes to 3, it doesn't really matter what direction, but if it goes from 3 from the right, x equals 3 is an asymptote because no matter what direction you go from 3 from the left, I'm talking about problem 2 there, x plus 2 over x minus 3. Okay, so when you substitute x equals 3, the numerator is a positive, it's a positive number, it's 5, but it's non-zero. So at x equal to 3, you get a vertical asymptote. And then, okay, so and number 4 there, yeah, well, the denominator is never 0, right? So it's just you get a kind of there's no discontinuities because yeah, the denominator of number 4 is never 0. Whereas, okay, well, 5, of course, you have a possible, which is the possible VA, POS possible, and VA vertical asymptote. Okay, so you look at where, so let's look at 5. You look at where the denominator is 0, and it turns out, well, it's 0 at x equal to 1 or x equal to negative 1. And well, it turns out, yeah, but the numerator is never 0, right? The numerator is never 0. And so, yeah, as x goes to 1, or as x goes to 1, you're going to get 2 over 0. Yeah, so you have an asymptote at x equal to 1 and an asymptote at x equal to negative 1. So so you get a vertical asymptote at x equal 1 and x equal negative 1, because in this case, at both those numbers at x equal to 1, you either have, in both those cases, yeah, you have 2 over 0. Okay, so here's one of my favorites, the cotangent of x. Okay, so we know the cotangent is cosine over sine. And so that where is the sine function equal to 0? Well, we know sine of 0 is 0. So, and the cosine of 0 is 1, right? So so x equal to 0, it's like 1 over 0. And it turns out that, I'm sorry. Yeah, so 1 over 0, yeah. So you get a vertical asymptote. So I graphed it for you. And so as x goes to 0 from the right, and you can just, okay, so when you go from the right, okay, so when you go from the right, okay, so that the cosine function is positive and the sine function is positive. Okay, so you get a positive, you get a positive, it goes towards infinity, right? You get a positive number over positive, but the sine function goes towards 0. Okay, so you're dividing 1, so cosine of x over sine of x, as x goes to 0 from the right, it's 1 divided by a very, very small positive number. So you get a positive, so you get the vertical asymptote goes towards infinity. Okay, so but let's say you go to x from, let's look at the cotangent function. I graphed the whole thing down here for you. So now let's take the limit of the cotangent function as x goes to 0 from the left. Now in this case, well, of course, the cosine goes to 1. But the sine function, okay, well now for x less than, you're close to 0, but you're negative. Okay, so remember sine is the second coordinate on the unit circle. So when you're going, so in this case, you're rotating clockwise. So x is a very small negative number. The sine function is negative, right? So you're going from x to 0 from the left. The sine function, because a very small negative number, so it's 1 divided by a very small negative number. So the graph of the cotangent function goes down to negative infinity, and you can see that right there. So look at the y-axis right there. The cotangent function, when we come from the right, is going up towards positive infinity, and is going down towards negative infinity as we go to x from the left. And the other thing that you can see is that the cotangent function, in case anyone's listening, the cotangent function is my favorite function. Anyway, so the cotangent function, yeah, tangent's my second favorite. Okay, the cotangent function, yeah, it actually has an asymptote at all multiples of pi. So because that's where the sine function is 0, right? So multiples of pi, 0 pi, 2 pi, 3 pi. Okay, what you're going to have is for the cotangent function, you're going to have a non-zero number, right? Because the cosine is either, even multiples of pi, cosine is 1, and odd multiples of pi, cosine is negative 1. So multiples of pi, you have a non-zero number divided by a 0. So that's why all multiples of pi, cotangent has a vertical asymptote. And of course, we know that it's multiples of pi over 2, no, odd multiples of pi over 2, we know that the tangent function has asymptote. So just make sure you can, I would definitely, we don't necessarily need to know that a lot now. Somewhere in I see I'm typing here, I'll fix that. Somewhere in your math career, in your calculus career, it's really very useful to know where the asymptotes of for tangent and cotangent. I think that's it.